All right, people, let's do another video on covering spaces, which is this is basically the follow-up to the one we did on a universal cover, and in this one we will explain how to construct the rest of the covering spaces in some sense, at least the path connected ones, I guess. So what is the situation? So all along, we've been looking at the following thing in this course. So we are in the world of, in the category of pointed topological spaces. We apply the fundamental group, and that lands us in the world of groups. Right, and so that's what I mean. At the level of objects, you are just taking the fundamental group. At the level of morphisms, to every continuous map between pointed topological spaces, you assign to it the induced homomorphism. And kind of the question motivating what we're doing is, well, if you give me, if you have groups, then okay, you can look at subgroups. And what is sort of the natural question, like the natural analog at which you should look in pointed topological spaces? And the answer is that to subgroups, one should correspond covering spaces. And what we already did was basically show like, okay, if I fix as my subgroup, as my favorite subgroup, the trivial subgroup, then my favorite covering space will be the universal cover. And the question we want to answer now is, if you give me some other subgroup, how to construct a covering such that, well, yeah, tau star of the fundamental group of the covering space is G. All right, so this proposition says that you can always do this. So given G, there does exist a covering space as such that the push forward of tau applied to pi 1 of x tilde is G. Well, it's G, and additionally, I mean, this is truly an isomorphism, so these two groups are becoming identified. So this is isomorphic to G by tau star. And how do we do this? So we start by taking the universal cover. And in particular, I don't want to get any sort of model of the universal cover. I really want to get the one I produced in the previous video. So we want to x tilde tilde, q tilde tilde universal cover to be the following thing. So this is, of course, the all the classes of paths starting at q. And q tilde tilde represents sort of the base point there, which is the constant path at q. And what is the idea? So why did x tilde tilde have no like trivial fundamental group? Well, the idea was that basically x tilde tilde is basically an unwrapping of x by the fundamental group, right? So basically, like all the loops in the basis space, they've now, they are classes of loops, in particular are classes of paths, so they've become points now in x tilde tilde. They've become the points that lie over in the fiber over q, right? So now when you have like a loop in the base and you lift it up, now it's not a loop anymore, right? Because basically what that loop does, it ends up in the point representing the class of the loop. So that is sort of like the idea of unwrapping. And if you want to construct now a covering space that is not fully unwrapped, right? It has still some fundamental group, G in particular. What we have to do basically is we take the universal cover, which is the full unwrapping, and we just wrap up partially, and we wrap up exactly G. How do we do this? So here's the formal definition. So to wrap up, basically we want to take a quotient. So x tilde tilde we quotiented out by the following relation. So we say that two classes of paths, gamma, the class of gamma and the class of nu, both in x tilde tilde, are related if when I take nu and I post concatenate it with the reverse of gamma, I land in G. Let's look a bit at this. So for instance, and a particular example would be like, when, let's say gamma is the class of the constant loop, then when is the class of nu equivalent to the class of the constant loop? Well, then that means that nu concatenated with the constant loop, so just nu, is in G, right? And this is exactly the wrapping we want to do, right? Like we want to say like, if we have an element in G that corresponds to an element in the fiber over Q, right? And that means that when, like, if I take a loop in G in the base and I lift it up, and I lift it to the universal cover, it has become unwrapped. So now by saying, now what you are basically doing is you're taking this path that is the lift, and you're collapsing the endpoint back to the class of the constant loop. So now you're basically closing it up again, so it does become a loop again in X tilde. Let's look at another case. So the general case is like, well, if I have two paths, nu and gamma, when are they related? Well, I mean, this expression in particular, it only makes sense if nu and gamma have the same endpoints. So okay, so these two must have the same endpoints, and now that they have the same endpoints, when I compose them, I concatenate them, they form a loop. And what I'm asking is that this loop is in G. All right. So what you can check is that this is indeed an equivalence relation just by observing that G is a subgroup. And therefore, okay, this is a quotient, truly. So we can define the quotient map, we denoted by pi, from X tilde to X tilde. And now what you can check, as we said, is that, well, these two things, they can only be related if they have the same endpoint. That means that even after the quotient, the endpoint is well defined. But the endpoint is precisely the covering map of X tilde to X. So that means that the covering map descends to a map from X tilde to X, and we call this tau. Having this map defined, all we have to check is that this is a covering map, and so we have to check how does like the topology in X tilde look. So let's say we have gamma and we have nu, well, they're classes. What does what does a neighborhood of each class look like? Well, a neighborhood of gamma could be, for instance, given by some open VT in X. So it looks like all the paths that do first gamma and then a tiny thing in VT. And an open neighborhood of the class of nu looks essentially like nu and then a little path, also in VT. These two opens, they become identified once we project down to X tilde. And why is this? Well, okay, so let's say gamma concatenated with nu, now it's in G. Then the same is, so these two are related. Then the same is true for gamma concatenated with the red thing and nu concatenated with the red thing, right? Because nu concatenated with the red thing with the reverse of the red thing with nu with the reverse of nu is the same as gamma concatenated with the reverse of nu, and therefore it's also an element in G. So yeah, they're related if and only if these two are related. So what that tells us basically is the following. So it tells us that an open in X tilde looks exactly like an open in X tilde, which looks exactly like VT, essentially. So an open in X. So this is the covering map. Right, so okay. So X tilde is a covering space. That's great. Now, what I've defined the covering space. Now let's define our favorite base point. So the only natural choice, of course, is that I take the base point in the universal cover and I project it down. Let's note this by Q tilde. Now, what does Q tilde represent? And here indeed, we should recall that Q tilde is the class of the constant loop. So Q tilde is represents all the loops that are equivalent to the constant loop. So it represents all the elements in G. And for this reason, quite often, when I write the favorite base point in X tilde, I will just write G for it, because it represents all the classes of loops that are in G at once, because all of them have been quotient out to be the same element. All right, so what do we have to prove now, what is left, is we have to show the claim about fundamental group. So let's go down to here. How do we do? So, well, we have to prove two things, right? So we have to prove that we have to prove that the image of tau push forward is contained in G, and then we have to prove that in fact this is an isomorphism, so that this map is injective. And how does this work? So let's start by proving the containment first. So I take any beta in X tilde, any beta tilde in X tilde, based at Q tilde, and this is a loop in our covering space, and I project it down to a loop in the base. And now, just as we reasoned for the universal cover, what we see is that, well, beta tilde is the same as the loop given by by the loop that goes from Q to beta of t, essentially. And what that tells us is what? It tells us like, well, what I want to check is where does the image of the class of beta tilde lie? So what is the image? So this is exactly here. This is of course the same as the class of beta, right? Because beta, well, it's just the image of beta tilde by tau, really. Then by this equality here, we know that this class is the same as the class of, is the same as beta tilde 1, right? Because beta tilde is a loop. But now by definition, what does it mean? So beta tilde 1, it ends up in q tilde, which is the base point, but q tilde represents an element in G. So that means that this class lives in G, which is exactly what we wanted to prove. The image of the push forward is always in G. Conversely, how do we prove that every element in G can be obtained as a push forward? Well, we just lift. So you just take a class in G, you lift it up, and by definition, it will be a loop, right? So we always know that by the homotopy lifting property that if I have some beta, a loop in the base, I can always lift it up to a path. And why is it a loop? Well, it's a loop because it ends up in some element in G by definition. So, but the elements in G have been quotiented out to be all the same. So therefore, this closes up to be a loop. And this is exactly it. So it's a pre-image. All right, so that's it. That is how you construct the covering space we wanted. The corollary out of this process, out of the argument, is that just like the fiver of the universal cover is isomorphic to the fundamental group of the base, the fiver of the covering space we just constructed is isomorphic to this quotient, right? And this is sort of natural because basically you're taking the original fiver of the universal cover and quotienting it out by G, right? And this is sort of the idea you should have in mind. So what has happened now? So now we had our subgroup G. Our subgroup G becomes the fundamental group of the covering space, and its fiver becomes the coset space. So sort of they're like the two sides, they're like the opposite or so, right? So we proved the existence of the covering space. Now we want to prove the uniqueness, just like we did for universal cover. So what is the statement? So if I have two path-connected covering spaces, x tilde and x tilde prime over xq, and both of them, the images of their fundamental groups are the same, so they're like the group of interest, let's say G, subgroup of interest G, then in fact these two covering spaces are isomorphic, right? And maybe a word of warning, so this equality here really means equality. So this is an equality as subgroups of the fundamental group. This is not an like an isomorphism as abstract groups. So for instance, subgroups of the fundamental group that are conjugate will yield different covering spaces. Different as pointed spaces. We'll see this a bit later. So what is the proof of this? So the proof is the same as before. So you just see both covering spaces on top of xq. And now because this leg is a covering map, I can lift tau. And now because this leg is a covering space, I can lift tau prime. So we can do the whole game of, well, now saying like, look, oh, then this composition is a homeomorphism that is in fact identity, and this homeomorphism is in fact a composition that is in fact identity. So these two are homeomorphisms that commute with tau and tau prime. So basically we're proving that these two covering spaces are equivalent up to isomorphism of covering spaces in the sense that we defined before. And what is really important to remark is like, okay, so formally this proof looks exactly the same as what we did for covering space, but we're like, the key thing is that we're using our assumption, right? So our assumption is that the images are the same, and this requirement is exactly what you need to have the homotopy lifting property, right? That this is the only thing that guarantees that tau and tau prime can be lifted. Okay. Very good. So we've proven existence and uniqueness of the covering spaces. Now we are gonna explain a slightly different way in which you should be able to think about covering spaces, which is the following. So let's say this. Let me give a bit of background. So let's imagine okay, what we've said is, okay, let's take the universal cover. How do you recover the basis space from the universal cover? Well, you just quotient out by the whole fundamental group. How do you obtain the covering space corresponding to G from X tilde? Well, you just quotient by G, right? So a way in which you can also do this thing is as follows. So you take your universal cover. This is like, yeah, simply connected and so on. And you multiply by what you want your fiber to be, right? So we've said that we want like the fiber of the covering space with fundamental group G is exactly this coset space. So you take your universal cover, you multiply by what the fiber is gonna be, and you then quotient out by the full fundamental group. Okay. Let me be a bit precise about what this means. So recall that, of course, X tilde has an action of the fundamental group, which is the tautological action by pre-concatenation. And now observe that also this side has an action by the fundamental group. But you have to be a bit careful. So I think this is commented a bit later on in the lecture notes. But the action on this side is an action on the left, right? So in this group, like this is, I mean, right, like this is not a group anymore, right? We've quotiented out by G, with where G is acting on the group on the right. So as such, we cannot anymore quotient from the right because sort of things won't be well defined unless G is normal. So now, but so we can do is instead act on the left. So let me be a bit careful. So basically, we say that a path gamma here and a class nu here is equivalent to another class gamma pre-concatenated by some path beta, by some loop beta in the fundamental group, and another class here where nu is post-concatenated by beta. And I claim that if you try to do the same by pre-concatenating, this is not well defined. Think about this. This is just a fact about about groups and quotients and so on. All right. So the claim is that this thing is a covering space, this quotient, and it's exactly the same we've constructed before. So in particular, its fundamental group is G, and it has pi 1 over G sheets. All right, let's look at the proof. All right, so what do we have here? So let's look at the space we have before quotienting. So this is just a product, right? This is just a set, and this is the universal cover. So as such, this is essentially just a covering space that is not path connected and has this many copies of X tilde as like different sheets or so. Here I've given each sheet a name, right? Because basically, I mean, each sheet is basically an element in X tilde times some gamma for times some nu for nu fixed. So, and these nus, they are elements here. So basically, I'm saying that if I have two different elements, two different loops, and they represent the same class in the quotient, then in fact the sheets are the same. All right. Now, what happens when I take all these many sheets and I quotient them out by pi 1? So the first observation is that if I take this sheet corresponding to nu and I apply a beta as explained here, then these two things will be identified, right? Basically, the element gamma here will be sent to gamma pre-concatenated by beta in this here. So basically, all these sheets, I've put many of them, but after the quotient, they will become identified. So I can just work on a single sheet. So let's take just the sheet of the constant loop. And now after I've done this, I mean, I have just to look at what the quotient does on this. And the elements beta that do not move this sheet are exactly those in G by definition. So that tells me that I'm just back to the original situation where I have a single copy of X tilde and I'm quotienting it out by G. So this is Y again. All right. So that's a little technical lemma. And there, I mean, you may wonder, why am I doing this? Because, I mean, if you think about this, all this proof is saying is, instead of taking X tilde and quotienting directly by G, what I do is I take X tilde, I add the coset space, and then I quotient by the whole thing. So it's like I'm adding more stuff that then I quotient out. So you might think this is kind of redundant. Why do this at all? And the reason is that it motivates the following lemma, which says the following. Suppose I have the fundamental group and it acts on a set S, and this is an abstract set. This is not a coset space anymore. This is whatever. Then you can do the same construction. You can take X times X tilde, the universal cover, times S. You can, on this side, you act on the fundamental group by preconcatenation. Here you use the action given by hypothesis, and you quotient out. And now this will be a covering space for the same reason we've outlined here. And by construction, it will be a covering space with cardinality S sheets, and this may be disconnected. So basically, if you go to Hatcher, what you can see is that he uses this to classify, to discuss like all the possible covering spaces of X, where the covering space may be disconnected. And the way to do this is because, well, you take S arbitrary, so you can have like pi1 sort of doesn't mix the whole set S, it keeps some parts fixed, and those will correspond to connected components and so on. Again, this may not seem very interested because, of course, disconnected covering spaces are just like disjoint unions of connected covering spaces. But this is a very general statement. So at some point, probably in future courses in the masters, you will see that basically if instead of having a set S, you have maybe a topological space and it's acted upon by the fundamental group, then out of it, you will be out of this process, you will be able to build something called a flat bundle. Again, yeah, this is not important what it is at the moment. I mean, if you know what a fiber bundle is, then okay, it's an example of this. But sort of, let's say it's a very interesting construction in many places of mathematics somehow. All right, let's move on to the next topic. All right, so in the previous video, we already studied the deck transformations of the universal cover. We saw that the deck transformations are, okay, they basically correspond to the elements of pi1. Let me recall the definition. So if we have any covering space, not necessarily the universal cover anymore, then a deck transformation is a homeomorphism of X tilde that lifts tau. All right, and as we said before, basically a deck transformation is an isomorphism of X tilde in the category of non-pointed covering spaces, right? So the first observation, of course, we already did say this, is that the deck transformations from a group, right? So here this just says, well, if I have a covering transformation, a deck transformation, sorry, F tilde, then its inverse is also a deck transformation, right? Just because of this reason, it also lifts tau. And if I have two deck transformations, we can compose them, and the resulting object will also be a deck transformation. Very good. And so the defining property for deck transformations is that there's not very many of them. There's only as many as elements in the fiber over a point. And why is this? Well, let's say I have two deck transformations, F0 and F1, and they both map X tilde to the same place. Then what have we said? So both of them are lifts of tau, and both of them map a given point to the same point. So that means that by the unique lifting property, they must be the same, right? Because once I've lifted one point, then all the others are determined by the lifting property. So that means that once I fix the image of one point, then the two deck transformations are the same. And so that proves the claim that we said, that there's only as many deck transformations at most as sheets of X tilde. Another question is when? Well, when is this an equality? And then we are going to give this a name. So we say that the covering space X tilde is normal if we are able to map any 2 points in the preimage of Q to each other by a deck transformation. So basically, deck transformations act transitively, let's say, in the fiber above Q. And in particular, basically, this says that equivalently, that there's as many deck transformations as sheets, right? Because you're able to move any sheet to any other. Now, how may this fail? So let's look at this the following discussion. So what we know already, right, is that out of our discussion about the universal cover, is that x tilde, the universal cover, is normal, right? Why? Because its fundamental group, no, sorry, its fiber over Q is exactly isomorphic to pi 1, and its deck transformations are also isomorphic to pi 1, and the action of the deck transformations on the fiber is sort of the tautological action of pi 1 on itself, right? So, okay, this is normal. Now, you may think like, well, okay, so we have an action of pi 1 on x tilde. Maybe we can try to use this action to define an action also on the covering space y, which is x tilde over g. And let's see why this is problematic. So let's suppose, what do we want to do, right? So I want to check whether I can extend the action of pi 1 to y. Oh, sorry, I don't know why there is a y tilde here. There should be just y. Right, so maybe let me erase that from my notes for later uploading them. Give me 1 second. Right, so so we want to see how could I define an action of pi 1 on y. And so, okay, here we have some f, some element in pi 1, and here we have the class of h, and this is an element in y laying over the fiber over q. Now, this is a class, right? I mean, so here this y is already a quotient. So this h we can represent by two different things, h0 and h1 in pi 1. And saying that they represent the same class basically means that, okay, that h0 can be expressed as h1 multiplied by something in g, right? Because y is exactly the quotient by g of x tilde. So now you may say, okay, how should f act on such an object? Um, yeah, and okay, maybe, well, let me say one thing. Well, okay, I will explain now. So then you may say like, okay, what is the action of f? So the action of f is just multiplication on it's like, it's pre-concatenation, right? So the action of f on h1 is this, and the action on h0 is this. But we've just expanded h0 of f to be this. And now we see that the class of this object may not be the class of this, right? Because it's not clear whether this multiplied by some element in G is this, because this element G is in the middle and I cannot pass it to the other side, because there's no reason why F commutes with G or F commutes with the group G, big G as a whole. The only way to obtain that G can pass to the other side for every F essentially and so on is that, no, sorry, not for every F, so that this passes to the other side for every G is that F should be in the normalizer of big G, right? And this is essentially the argument. So what this has shown for us is that, sure, we cannot define an action of pi 1 on y, but at least we can define an action of the normalizer of G in y, right? Just because then in that case, these two things do define the same class. And this is exactly what it is. You just take a class in y and you pre-compose it by f, right? That's pretty great. And some of you may complain like, well, I mean, here you wrote some h, so why are you not acting from the other side? And the reason why I'm not acting on the other side is that I mean, here, for instance, I took loops, so that's okay. Here, like, I could pre-compose loops on the other side, but y in general is a space of equivalence classes of paths. So f only can act on the right. So I have no choice. So this right action is the only action I can possibly take. All right, so y has an action of the normalizer, and now we have the following statements. So first of all, y is normal if and only if the number of sheets is the number of deck transformations. This we've already discussed. And if and only if the group G is normal. Okay. And this is the reason why we call this condition being normal, because it corresponds to being a normal subgroup. And this is because of the reasoning here. And instead of giving you a proof of this proposition, let me give you a more general proposition, and then I think that's the end of today. So the more general proposition says the following. It says the deck transformations of the covering space Y we just defined is isomorphic to the normalizer of G over G. And what our lemma above proved is that there's a map, right? There's a map from the normalizer to the deck transformations, right? Because we showed that even though we could not define an action of pi1 on Y, we could define an action of the normalizer. Furthermore, what is easy to see is that sure, we defined this action for the whole normalizer, but in fact, the action of G is just the trivial action, right? Why? Because, well, the classes in Y, they've already been quotiented out by G, so when you do it again, you're doing nothing. So this part is, so we quotient out so that we have a monomorphism from this to here. So the question at this point is, well, is this map an epimorphism? Is this map surjective? All right. All right. So what is the argument? So, so as we said, like deck transformations are characterized by what they do on a single point, right? So, for instance, all the deck transformations we've constructed out of NG, of course, what do they do? So basically, they take the base point, which is G, and they send it to the class of nu, right? So to conclude, the argument is like all the deck transformations we know do this. So they just map the base point to some element in the normalizer. So it's enough if we prove that every deck transformation must take the base point to a normalizer, because then we will be done. So let's look at the following diagram. So let's suppose I have some deck transformation. Let's call it psi. All right, and so this is, and I'm gonna look at its action, like at the level of fundamental groups. So let's say here I have the fundamental group. Let me see. Let me see. Yeah, I see. So let's suppose I have some deck transformation, psi, and this deck transformation takes the base point G to the class of gamma for some gamma. So what I'm gonna show is that gamma is in the normalizer. How do we argue? Well, okay, then I'm gonna take the inverse. It's kind of more comfortable for this argument. So I take the pi1 at this other point. It maps to the pi1 at the base point by the induced homomorphism inverse. And then we have the both projections. Since this is a deck transformation, then this diagram is commutative. And now what do we have? So on the one hand, if you walk the diagram on this direction, what is the image of the fundamental group here? Well, it's the image is you first go here, and now you take just the image of this part. This is an isomorphism by assumption. So the image of this is just good old G, right? So this is just because we factor through this part, we know the image must be G. Now let's look the image directly by tau, right? And let's write it in the following way. So here we have the fundamental group at gamma. And what is gamma? Gamma is some class of loops, right? And this class of loops, I mean, we've represented, I mean, this class of loops is not in G, supposedly. So what we can do is do like what we always do, right? Like, so we have, I mean, let me say it like this. So we have the fundamental group of Y at two different points. We have it at the base point G, and then we have it at the base point gamma. Now, how do you relate them? Well, you relate them then by a base point change, by following, by conjugating by a path. What should this path be? Well, the path is exactly the class of gamma, right? Or rather, it's left in some sense, right? So basically, you take the elements in this fundamental group and you pre-compose them by this lift of gamma, and then you post concatenate them by the reverse. And what this is telling you is that this is some conjugation, and now you push it forward. But when I push forward, what has happened? So this part inside, it maps to G by assumption, but this goes to the class of gamma, and this goes to the class of the reverse of gamma. So that means that we're getting some other group. This group and this group don't have to be the same in general, because when you conjugate a group, you don't always get the same. You get the same if and only if gamma is in the normalizer. And that is the proof. What you should take out of this is that all these proofs are really proofs about group theory. Like, in some sense, what we are just doing is putting topology in the group theory. So in some sense, all the proofs feel a bit like just algebraic. So let me maybe close this proof by saying, okay, this is a complete proof. Probably here, I should be a bit careful with this notation and denote this by lift of gamma tilde or something like this. So I will replace this for you. And that's the end. So essentially, I think that covers most of the material for covering spaces. You can still expect a couple of videos after this. Hopefully, still, I think still this week, maybe in a couple of days, um, about, well, some additional exercises, some additional material that it's just basically an excuse for me to give you a bit more feeling out for this topic. And then we're done with the course. So, well, yeah, thank you for watching and see you in the next one.